I'm Nick. I'm going to be giving a talk on fault-tolerant command and control networks today. So here's the agenda. Intro, going to go over a little bit of botnet history, a little explanation of what C2 is, a little in-depth on how a very common form of C2 is used, and then an idea for a C2 network that was inspired by IRC. Not using IRC, but inspired off of how IRC works. Then the goals for the project that actually came in my head, and then a little bit of a demo, and then questions and special things and references. So who am I? Nick, that's me. Fourth year BSMS, Computer Security, RIT. I was the tech lead and vice president of RC3. If you don't know RC3, it's RIT's Competitive Cybersecurity Club. Last year, and then this year I'll be the vice president again. I was the captain of RIT's first ever collegiate penetration testing team. We're going to hopefully do that competition again this year and do some fun stuff, and I'm looking to get into more pen test stuff, which is kind of why my head was wrapped around botnets and such. And this is my first talk at a con ever. So, woo! Woo! Yeah! So let's talk a little bit about what's in scope. Basically, we're going to be talking about command and control servers, how they communicate with each other and the clients. It's mainly going to focus on server-to-server communication and just a little bit of client check-in. What's not in scope are the clients in general. I'm not going to go in depth on how the clients are going to be managing the callback domains, not going to be managing them, how the clients are going to be connecting to the network, just how the network is going to facilitate the clients. I'm also not going to be going into any reverse engineering on clients to make sure that you don't expose these domains. In other words, your implant is bad and you should feel bad is not something that will be covered in this talk, and I don't want to hear. Cool. So, a little bit of an overview on botnets. Right? Wikipedia states a botnet is a whole bunch of computers that talk to each other, this long-winded stuff. Basically, it's a whole bunch of computers that talk to each other or servers that give them information on things to do. So you can have a malicious botnet or you can have a benign botnet. There's the infamous Zeus banking Trojan botnet, which exfiltrated tons and tons of bank credentials and bank information and money, right? Or you can have something that's benign, like SETI at home. If you don't know what SETI is, it's a whole bunch of people in South America, I believe, that have big satellite dishes and they listen to space to see if aliens are talking. And that's a lot of data because you've got to process a whole bunch of signals with, I don't know, patterns that aren't specifically developed and stuff, so they outsource it, right? So you can sign up for SETI at home and basically enlist yourself in a botnet, right? It's for SETI, it's for science, right? But ultimately you're still in a botnet. You're still receiving commands from some sort of network. So what can we use a botnet for? A lot of what we see today is for DOSes, denial of service. You have a whole bunch of machines hammering a website and bringing it down. Email spam. Once again, leverage a whole bunch of machines to send as much email as you want. You could use it to seed torrents from, let's say, a leak. So let's say you leaked something like the Panama Papers recently. You've got terabytes of data that you're trying to get. You seed it out to all of your clients. This ensures that, hey, these documents that you've leaked out always have somewhere to go down and they can't be brought down by some sort of DMCA, where they go and just take down the one or two servers that you're seeding off of before it gets distributed out to everybody who has it. Or we see a lot of this nowadays, botnet as a service. So you build a botnet, you get it as big as you can, and then you just hire yourself and have people hire you so that you can do whatever they want to do. So you say, okay, we'll let you, this other criminal organization, use our botnet to denial of service this site. So just a few figures. One of the first botnets that, just figures from Wikipedia that they listed, the Bagel botnet had about 230,000 nodes. Infamous Configure, that's where we see MS08, 064, 067, that's right, MS08, 067, one of those exploits. There was millions and millions of nodes that were in that net, with a portion of them that were in a botnet. And then the Zeus malware, there were about 3 million nodes in the US alone. So let's get into some of the terms that we're going to be using to describe botnets, right? We've got bot masters, C2 servers, relay nodes, bots, and I'm going to get into all of these. And normally we have something that's organized like this. You have the bots at the bottom, relay nodes in the middle, C2 servers right there, and then up at the top we've got the master, and I'm going to go all into these from the ground up. So we're going to start with the bots. Right? The bots, or zombies as they're sometimes called, is the malware that you have installed on the target. It's sitting on the target, waiting, calling back, getting your instructions, and then executing whatever you want. It checks in, it sees, okay, I have a DOS command for this for X amount of time, get this command, perform it, wait, check in, wait, check in. Ideally, you're going to have a lot of them, because what is a botnet if you only have two nodes? You're not going to get too much accomplished with 2 nodes out in the wild. And ultimately, it's to execute the commands that's given by the C2 servers. C2 stands for command and control, if I didn't make that clear. So we're going to move on to the relay nodes, right? So the relay nodes are for forwarding connections from the bots to the servers. Ideally, you don't want to expose your servers, because if you only have a few of them, like this diagram shows, we have, let's say, 3 servers in this network. The bot master looks like it's updating each of those individually. You really don't want to lose those, right? C2 servers are kind of like your crown jewels. You don't want to lose them, so you spin up a whole bunch of relay nodes that facilitate communications from the bots to the servers. This could be as simple as like a SOX proxy, or like netcat forwarding, listening on one port, forwarding it out the other, and just facilitating a communication. Or it could be as complex as rotating through hundreds and hundreds of domains, or having a domain generation algorithm that the attacker is going to register certain domains that are going to lead back to those servers. And this is the layer in the traditional model that you want to be fault tolerant, right? You want to have a lot of these so that if you lose 50 of these relay nodes, you still have 100 of them left, and the malware or the bots still know how to get to the layer of relay nodes, which know how to get to the C2 server layer. So onto the C2 servers. So these are going to be holding all of the commands. It's going to be accepting connections from the bots through the relay nodes, or if you don't have a relay node network set up, it'll be accepting connections directly from the bot. You can hold files there, commands, modules, whatever you have your botnet set up to do. And there's this idea of command and control channels, different methods of delivering the command. So let's say you have one set of relay nodes that says to call back over HTTP, and it downloads an HTML file, parses it, and that's your command. It could be HTTP or HTTPS. You could have one that operates over ICMP and just embed the data in like an ICMP echo request. And you could have multiple channels in the same network depending on how complex and how tiered you want to get your network. And then the bot master. This is the person who's controlling it. You're inserting all the commands, normally through some sort of web interface, or however your network is set up, you're putting the commands into the network so that your bots can execute them. You can divide the bots into logical groups if you so choose, but ultimately you're limited by what the botnet is built on. You can't DOS something if the code isn't written for it. So, on to C2 channels, right? C2 channels are the means of transmitting the information. Touched on this a little bit ago. Many different protocols. And the idea is to hide somewhat in plain sight. You don't want something that's super crazy obvious that's going to say, hey, this is me, I'm beaconing back to this C2 server. Like redteam.domain.whatever is probably a bad idea, or this is like AC2 whatever your domain is probably a bad idea if you're using DNS resolution. You want to look normal, right? And just some common protocols that you can use. IRC. Drawback to IRC is that it's plain text traditionally, so if you connect to the server, you see all of the commands being broadcast in plain text. You can see when someone checks in. But the advantage to that is there's multiple different actual IRC channels that you can go through. HTTP and HTTPS would be a really good option, probably your go-to option. I don't know of anybody that's going to be blocking web outbound, so HTTP and HTTPS would obviously be better because, well, it's encrypted. And just because you could do it over ICMP if you wanted to, probably going to get flagged real quick. You could even try and do it over SSH or something that mimics an SSH session. So I'm going to go into a little bit of how IRC used to and currently is used by C2, some of the drawbacks and some of the advantages to it. So we have the client, like an IRC client, that connects to the server. In this case, it's going to be our bot. It's going to be connecting to a certain channel, right? So let's say we have pound channel 1, right, and it's going to be checking in, say, hey, I'm here waiting for commands. It's going to be relying on the IRC infrastructure to deliver the messages that a certain user is going to be putting in. So let's say you as the bot master would go and you would say, hey, this command now is to DDoS site A, right? All the bots that are listening on that C2 channel will be like, okay, that's my command. I'm going to do that, and they execute whatever module it is. Right? And you would have some sort of way to change channels every so often, whether it's through a command that says migrate to whatever, and then whatever bots are on there would just migrate to that other channel. Or it could be done automatically through the bot. Some of the advantages to using an IRC, it's pretty easy to set up. All you have to do is have a channel, and then have a pretty simple syntax that both the bots and the bot master understand. Easy distributed commands because you're relying on IRC's network, and kind of send it in plain English. It's easy to understand and easy to parse if it's your first thing to write. Disadvantages, you're sending it in plain English, right? Unencrypted communications, and if the bots aren't validating who's sending the command, then it's relatively easy to hijack and shut down the network or make it do what you want to do. So all of this was kind of mulling around in my head. I was kind of thinking, so I want to do something with botnets. I want to do something offensive, right? How would I set this up? What if I built my own, right? But before that, I was kind of thinking, I want to program something. Let's try IRC. It's a relatively simple protocol that's really well defined. So I thought, wait a minute, what if I combined the two, right? So I want to specify that I'm not using IRC for this proof of concept. Not just making a botnet that connects to a channel, listens to stuff. It's using how IRC, the protocol, is set up and defined to define the network of C2 servers and how they're going to be updating each other. So for a little background, IRC works as a spanning tree. There's never a group of nodes that are going to be set in a loop, or there never should be, right? If A, B, and C are all here, A and C should not have a connection if they both connect to B, because then you have a loop and bad things happen, and that's just how the protocol is set up. So why not use that, right? It's pretty set up. I could just fork IRC and modify it however I want, right? The problem with that is that we're going for redundancy at the C2 layer, right? So the whole idea is that you don't need the relay nodes. Oh, that's necessary. Yeah, there we go. Cool. Is that we don't need the relay nodes. We're focusing just on the C2 server layer right now.
Hey.
Cool. Imagine if you lose a branch that happens to be in the middle of your network of servers. You're going to end up causing network segmentation. You're going to have disjointed segments. So let's take this example IRC network, right? IRC, not the C2 POC that I've come up with. We've got 6 servers, 2 has 3 links, and they're all organized like that, right? So if someone on server 1 wanted to send a message to server 6, it would go through server 2, then server 3, and out to server 6. If someone on server 4 wanted to get out to server 3, it would broadcast to everybody, and the IRC server would only keep the message if it had clients that were on those channels, right? Want to send the message, it's going to travel along like this. It's going to get duplicated and sent out to the other ones, and it's going to get to there. So from 4 all the way over to 6, we can see the message was there, right? So imagine if we're going to lose one of these nodes. Let's focus on server 1, right? If we lose server 1, the clients on server 1 are just out of luck. They can't do anything, right? They can't talk to anyone else because the server's down, right? That's not too bad. We've lost an edge node, right? If we lose server 3, however, we're going to have a problem. So server 6 and server 2 are still functional, right? But we've lost server 3, which means we've lost the connection to servers 2 and so to server 6. So someone on server 1 won't be able to talk to server 6, right? And someone on server 1 can still talk to someone on server 4, but they can't get over there, and server 6 is in its own little world. The worst case scenario for this topology is if we lose this node, because we lose those links. Now we have 3 separate IRC networks that can't talk to each other. So that's kind of where I came in. So like, wait a minute, this spanning tree is a bad idea if we're going for redundancy at the C2 layer. So let's expand it to a partial mesh. A full mesh would be ideal, right? All nodes know how to talk to each other. Everything's amazing. You only need one update message, goes out in one broadcast. Everything's updated, and flowers and rainbows, yay. In reality, that's probably not what you're going to get. You don't want one node, or you don't want the ability for one defender to breach or watch one node and be able to know all of the nodes in your network, because then they can just say, hello, government, please shut these down. It's doing malicious activity, and here is the information about it. And you can lose your entire network in a matter of days. So the idea of the partial mesh is that we're going to be forwarding the commands to the servers, kind of like how we were forwarding with how IRC was forwarding. Yeah. So what we're going to ensure right now is that each server is going to have the same database. This is a short-term goal for the proof of concept. Proof of concept is not finished yet. It's far from it. I'll get into that in a little bit later. But if we have the partial mesh organized correctly, we can be tolerant of mild to medium losses. So let's say someone takes out 20 servers in your 60-server network. You still have the clients which know enough about the rest of the network to reconnect back to it. Let's just assume for the rest of this talk that the clients have an algorithm that says, okay, we know how to get to a different area of the network logically, right? So if a client on the left side of the network knows that there are nodes in the middle of the network and the right side of the network, let's just assume that the clients know how to get back to the network, right? But we got to remember, if someone dismantles 85% or more, a huge number, there's not really going to be much that you can recover from. If you've got 10 servers in high availability and 9 goes down, you're going to have a bad time on that one server that's left. Yeah. So some of the design choices, Golang. If you don't know about Go, it was developed and released in 2006, I think, 2006 or 2007. The year's escaping me at the moment. But it's a compiled language. It's open source, managed by Google. It's got a pretty decent syntax. It's kind of like if C and Python had a baby. Yeah. So one of the problems with this thing that I'm going to be showing you, my idea for the proof of concept, is that redundant messages are going to be a problem, but the way I'm going to solve that is that the servers are going to silently ignore it, and that's going to become a little more clear in a little bit. Why did I choose to go with the way I'm about to show you? I felt it would have been easier than just implementing a full peer-to-peer routing mechanism on a server that I'm going to be deploying in random places. I could use Batman. If you're not familiar with Batman, it's the better approach to mobile ad hoc networking. Basically, it's a layer 2 ad hoc networking protocol that's actually built into the Linux kernel now that facilitates ad hoc networking and routing. But I felt that that would probably be a hard thing to do in Go, and I'd probably have to write my own libraries. So let's just go with the partial mesh and the forwarding and the silently ignoring the redundant messages for now. That might be a later work. And there's this idea of a partial information chain versus a full information chain. For right now, we're going to define the information chain as the servers that are going to be receiving an update. Partial is going to include just the servers that are going to be receiving. A full information chain would be all servers that have received and sent the message. The problem with that is that you're going to increase traffic size exponentially. With 1 or 2 nodes, it's not that big. But if you have a 50-node network, you're going to have a whole bunch of servers saying, hey, 1, 2, 7, 8, 9, 57, 36. I've all seen this, and a whole bunch of servers are going to be sending it around. It's pretty conspicuous. It's pretty easy to see. So the algorithm that I have for the servers is going to be that the server is going to be establishing peer connections with other C2 servers. Whenever there is an update to the command database, it's going to notify all other local peers. The servers are only going to be knowledgeable of other peers that are in the network locally. One hop away, it doesn't know anything more than 1 hop. So for the peer-server connection, peers are going to contact each other. Ideally, it's going to validate each other's authenticity. A long-term goal that I have for this is to be able to turn it into a framework, say generate a key at the beginning, and that you have a TLS key or a TLS cert that's going to be valid for each of the nodes, and if the cert doesn't match, you don't connect to the network or don't accept any communications from other nodes in the network, so that it's resistant to hijacking. And you can either do it at a periodic interval, so you could do it like an HTTP/HTTPS check-in, or you could have a constant session, like mimicking an SSH tunnel or something like that. So whenever the command database is updated, whether it be by the master or whether it received an update from another client, we're going to ignore any message that's duplicated. It's going to save, for now, all messages that are there. And then the server is going to be notifying all of its local peers. And for the server updates, it's going to update all other peers that it did not receive the message from, right? So if we have servers A, B, C, and D, and B is connected to C, D, and A, so we've got 1 in the middle and 3 on the outside, if A sends an update to B, B is going to send it out to C and D, but not A, because it knows that it got it from A. So we don't have an infinite bounce between the nodes. And then each of those updates is going to contain the partial information chain, and I've got a bunch of diagrams that's going to display that later. So more information on the partial information chain. It's going to be containing the IDs of the server that the update's being sent to, and if the ID is listed as a peer, it's not going to notify that server, and it's just remember that it's ignoring duplicate updates silently. So let's take the simplest network that we can have, 2 nodes of the C2 servers, right? We have a message with the partial information chain set to 2 because that's the destinations currently. You can think of the partial information chain as the destinations for all the messages or multicast. So we send the message over to 2, and then it gets it. Yay, both of the databases were updated. So if we expand this, we have servers 1, 2, and 3, all organized in a line. 1 wants to send a message, updates the database, sends the message out to 2, 2 gets it, realizes that it can't send it to 1 because it got it from 1, and then it has to send it to 3 because that's the only other peer that it knows about. Then 3 gets it, realizes that the only peer that it has is 2, and will not send it to 2 because, well, that's the link that it came from. And then everything's happy and the databases were updated. So let's expand this a little bit. We have 4 servers now, and then there's a triangle that we have between servers 2, 3, and 4. Starting with server 1, it's going to be sending to server 2. So here's where we actually see where the partial information chain actually does something. So server 2 realizes that it has to send to servers 3 and 4 because those are the other peers and it can't send it back to 1. So it sends it out. Servers 4 and 3 both realizes that the other server is going to get the message at the same time, and then it says, okay, well, I don't have to send it because they're already getting it. And then everything's happy, right? All the databases were updated. So let's expand this to 6 nodes. This is essentially the IRC network that we had earlier, but instead of having 6 being isolated only to 3, we've now connected it to 5 so that we have this big loop. So we have an update that comes from server 1. It's going to go out to server 2. Server 2 realizes that it has to send it to servers 3 and 5, right? And then server 3 over there says, okay, well, I got it from 2, and I'm going to send it to 6. Server 5 says, okay, I've got peers server 4 and server 6, and I got it from 2, so I'm not going to send it to 2, right? So what we run into is both of the servers are going to be notifying the same target server, right? Server 4 is over in its own little world, doesn't have any more peers, that's okay, but this is where the silent ignoring comes in, and it's just going to silently ignore one of the messages. That totally looks green. No, it's supposed to be yellow. Okay, well, okay. So it's going to silently ignore one of the messages. So where does this idea of the fault tolerance come in? It's a combination of things. It's a combination of the command database updates and the command synchronization between the servers and the network. And it's reliant on the clients having a chain of domains to contact in the network, like I was saying earlier. They have the ability to contact far different areas of the network, so if one side of the network is taken down, the other side is still functional, and the client can migrate to another side. And the idea that, yeah, that's what I just said. So goals for the project. Short-term goals, what I have right now is that the server is going to be accepting communications from the client. It's a little buggy. There's going to be a default channel placement, and then later on there's going to be the ability to segment it off into, okay, so like these are going to be my DOSer bots, and these are going to be my data exfil bots that are going to act more like an implant that you're going to put on a target. You can divvy up commands because you don't want to be issuing DOS commands to your ones that are supposed to be sitting and hiding, right? You don't want a lot of traffic coming from those because it's saying, hey guys, look at me, I'm here, I'm doing bad things. Server is going to be responding to the client's requests, and that database replication across all the servers is going to be enabled by default. A later work that could be done is that it functions more close to IRC and that it doesn't contain any of the updates for clients that it does not have or channels that it does not have, and if it does, it queries the network to forward it. But that would involve a lot more of the routing, so there's some design decisions that I have to make down the road if I want to continue this any further and have those things. So for long-term goals, like I was saying, the TLS cert generation and the validation between all the servers to ensure that you can't just connect something into the network that's going to update the database saying, hey, I want you to ping all these addresses so that I can know where all of your bots are, and I want the C2 service to notify this so I can have someone take them all down. Full forwarding and database replication, and I'd like to make it into a big project and put a web administration panel on it. Have the ability to dispense different modules to clients. So let's say you have a generic client that's in there. You say, okay, well, I'm going to check into the network and I'm going to download this information, or I'm going to download these modules to perform persistence method X or persistence method Y. The whole idea behind Go is that it's a cross-platform language. You write things in Go, and it, for the most part, unless you're doing something extremely system-specific, is going to be able to work on different systems. So if you have an implant that's written in one of those networks, it can download things catered to the OS that it's on. Another big thing that I want to do is I want to make it into an HTTP or HTTPS C2. I, at the first part, decided that I was just going to do it with opening a raw connection and sending information. At this point, none of it's encrypted, but that's just a let's get it working before I actually organize things the way that I want to, and then maybe expand it into a potential framework for an automated deployment and make it an open source framework. To say, build a botnet. It could be useful for penetration testers who want to do some long-term engagements so that you have a network that you can build up and tear down and issue shutdown commands to your network. So things that definitely need to be improved a bit, using an actual database rather than just storing data types in memory. There's some janky code in there now that definitely needs a fix. And then currently the IDs for the clients and the servers have the same format. I'd like to differentiate those, maybe just add a flag in there that says if 1, client, if 0, server. So on to a little bit of a code demo. We're going to walk through some of the functions that I have set up right now. So over in this pane over here, no, you can't see any of that. Good. Yeah, you can not read any of that. Can everybody read what's going on? Kind of. Can someone flick the lights in the back? Maybe it'll be better. Hopefully. Better? Oh, good? Is everybody okay with that for like 5–10 minutes? Okay, cool. So, over in this left pane, I have 2 separate repositories, one for the server, one for the client. Over here, we have all of the server stuff. Launch the server. The server reads from a command file, so if we go into the commands directory, we can see that I have several things like add a command to channel, and that's going to be like a wget command or a ping command. Those are just the 2 commands that I chose to implement at the current time before I expanded into something else, so that I have the ability to transmit commands, and then it's just a matter of writing an execute function on the client. So if we see, we're just starting on a default port. Yeah. So we have the client, which is over here listed as the implant, and right now it connects to the server. There's a few debug messages in there, And right now we're seeing the HTTP GET right here, so we've transferred the message and we've actually got it to execute, but we get the error message saying we cannot get the URL 1.html, just as an example. And then when we request again, the client right now is set up so that it does another request every time you have the enter button. That'll obviously be changed. And I have 1 or 2 bugs that caused the client to crash. That came about like a day or 2 ago, and I cannot seem to figure out how to fix it. So I kind of have a little bit of a stunted demo right now. The server-to-server messaging is unfortunately not functional. I would have loved to show that. That's one of my biggest, oh darn, why didn't I get this working about this talk. So that's why I was trying to focus a little more heavily into the explanation of how it would go. I ended up getting most of the supporting things, but not the main thing. Oh darn. So we can go through a little bit of the code review on the server side. Cool. So for the server, we have this idea that it's going to be having an ID, it's going to be having a listener that it's going to be receiving connections on, a list of clients, a certificate, which at this moment is not being used, peers, the channels that it's going to be having, and forwarding and replication, those booleans. Am I going to be forwarding things on, or am I not going to be replicating the database? An idea that you might not want to forward some things on is maybe you have 1 or 2 servers that you've implanted in a target's network. You don't want the database replicating everything for things that aren't connected to that network. So you want something that you're implanting on the target's network to be a little more covert. So like I was saying, the ID generation function, it's basically slapping together a random number and a hash of the timestamp and then hashing those together. Currently those are the same. I should probably add another field to differentiate between a client and a server. At this point I just have it sending server or client depending on what it is to connect to each other. Yeah. So the channels are organized as such. We have a list of clients and a list of commands and ways to add clients, add the commands, and do as such. Currently, this is what I was talking about saying I should probably switch to something else other than just having an array in there. I should probably switch to using a database because it would allow me to actually support more and build out more. Currently the code only supports the first default channel in the server. Might be on time. I'm super early on time. So here's kind of the idea behind the commands for the current data structure. No, not that file. The idea behind the commands is that they have an ID associated with them, a description, and the parameters are going to be passed to them. Right now it's set up as a list of strings so that you can facilitate any command that you'd like to do. So right now the commands that I have only have one parameter passed to it, like the wget, you only need a URL, or the ping, you only need the target IP address or domain name, right? But what if I had something for copy the folder, copy the contents of these directories and exfiltrate them to my server? That's facilitating multiple directories or multiple lists of things. And when the information is transferred, it's going to be put into a JSON object and then base64 for transfer. And then it's labeled with a timestamp so that you know of when it's attached to the channel, the list of commands that are in the channel, it's going to look at the furthest rightmost entry, the last entry in the list of commands, and say what's the timestamp on that? Is that timestamp later than what I have? If it is, it's going to add it. If not, it's going to just discard the message silently. Yeah. So that is unfortunately all that I have for code. It is multi-threaded. So if we wanted to now facilitating multiple clients, so it is accepting those clients from there. But that is about all that I have for the code side of things. Cool. So does anybody have any questions? Why did I decide to do this thing in that way? What do I want to? Yeah, you can turn the lights back on. Thank you. Any ideas for the network? Open up to questions. Yes, Ed.
So, how does the fault tolerance work if, say, the link between if you go back to the example with, I think,
The 6 or this one?
Yes.
Yeah.
Yeah. So if you skip forward a few times until there's the 5.
The collision?
So when you hit 5,
Yeah.
it assumes that
Yeah, so 5 knows that it needs to send a 4 and 6.
no, it's the previous one. sorry.
Previous? This one?
Previous example. It's the 5-node one. I think
Oh,
one before
the
this.
4 node one, this one?
Yes.
Okay.
So if server 4 assumes that 3 got the message, but if the link between 2 and 3 is broken, how is 3 going to get the message if 4 assumes that 3 got the message?
That's another one of the shortcomings of what I had short of implementing the full peer-to-peer routing.
Okay.
So in lieu of implementing the full peer-to-peer routing, which would be an end goal for this, that's one of the drawbacks, is that if you do have a link down between one of them and there is some sort of loop there, you're going to get servers that don't have the message. And yes, that is a problem. Any other questions?
Does it matter what kind of client, like what operating system, how much, like what are you using as clients? Just virtual machines?
So for the client, it's a piece that I wrote, writing it in Go, just because. The idea is that it tracks whatever operating system it is. So actually, if we go over to, I'm just going to mirror displays now, but if we go over to the code, this is my client code. Right. So over here we have the execute ping, right? So there's a library for executing a ping command, and how it works is that you can say, hey, perform a ping, and then the Go compiler performs all of the operating system specific stuff. So that's the idea of you write it in a language that actually transfers to multiple different systems. That's one of the cool things about Go, is that a lot of it is designed so that you only have to worry about making it work for the Go compiler, and then it works for the other operating systems. It's not like Python, which compiles to a bytecode and then gets run specifically through there. It gets, and I guess it is down to a bytecode, and then the bytecode is specified within the compiler. So I guess there is a pre-compiler and then an operating system specific compiler. Any other questions? Yes, back there.
So a couple of things. Number one, did you consider using SNMP v2 or 3 to manage them? And that's number one. And number two, when you said that you want some of these servers, especially the DOS servers, to have a level of being not seen, can you put like a firewall in front of them to prevent unwanted traffic from getting into?
Could you say like the last half of that sentence? I couldn't hear the last half of that.
Can you put a firewall in front of them to prevent the unwanted traffic from getting in?
Yeah, so one of the ideas is that you would have the generic node call back to the network. The network would know, hey, any nodes that are coming from something that reverse DNS resolves to this domain name, or like the company that I'm trying to target. Let's say I'm trying to attack RIT, right? Anything that's going to be calling back that resolves to an RIT.edu address, I want to have this set of commands and be put into this channel. Or something if I'm trying to attack M&T Bank, or someone who comes from like a Time Warner Cable address, I want them to be part of my DOS location. So the server network would have the ability to differentiate, okay, based on these criteria, let's put this client into either the default channel, which most of them will be put into and will not be used as much, except for like updates and such to the bots, or based on where they're coming from, put them into a specific channel that you've created.
Go does all that processing? Like the scripting does all the processing?
Yeah, it would. So the end goal for that is to be able to create a rule set like that, say through web interface for the administrator, say, okay, anything coming from here, add to this channel that I've created, and give it just instructions on how to divide them to the channel. And that would Go right now is going to be the backend server. I may switch it to something else if Go ends up not being the proper language to do exactly what I want. But for the current term, yes, Go will facilitate all of that. Someone else had a question. Yeah, Brad.
You mentioned that you wanted to have the ability to push out updated modules for augmented performance of the implants, correct?
Yeah,
How do you plan on doing that, since Go, they compile statically to a binary, so you can't really use system libraries with it unless you're pushing out a system-based process or script with it. So how are you going to try and do the update system?
So the idea could be that the implant that you have is more of a driver for other pieces of malware that you have running or things that you could do. You could have separate scripts, you could have separate pieces of code running on the machine, but ultimately the implant's going to be more of a driver for things and facilitates those other tasks staying afloat. Any other questions? Okay, so a couple of special thanks. Thanks to Jamie for encouraging me to actually do this talk, and then Brad for introducing me to Go and general design assistance and such. Those are my references. You can reach me at these things. I literally made a Twitter like 2 days ago. There's literally nothing on it, but you can reach me there. And that's my email address. So that is all I have. Thank you for coming to my talk.